Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 23, Book 9.6, Hierarchical Generation. From quantum whispers to cosmic paragraphs. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are stepping across a new and essential threshold in Episode 9, the generative grammar. Our journey has taken us from the alphabet of phi to the dynamics of its stories, and then into the computational heart of its production, a heart that beats with chaos and novelty. We have seen how the universe writes complex, ever-new sentences from simple seeds. But as we stand amidst this overwhelming, churning novelty, a practical question arises. How do we make sense of it all? The world we navigate is not a cacophony of fundamental chaos. It is structured. It has levels. Atoms form molecules, molecules form cells, cells form organisms, organisms form societies, planets form solar systems, stars form galaxies. At each level, distinct and reliable rules seem to operate. The rules of chemistry are not just watered-down quantum physics, they have their own logic. The rules of fluid flow are not just the agony of tracking a trillion molecules. They are elegant equations about pressure and velocity. How does this hierarchy of order emerge from the single foundational narrative of phi? Today, we enter Book 9.6, Hierarchical Generation. We begin with Part 23, Scale-Dependent Productions. We will learn how the holophase grammar, when viewed at different zoom levels, appears to speak different dialects, each with its own effective rules, all while remaining faithful to the one true tongue. Our anchor image is a vast, detailed geographical map. Imagine you are looking at a map of a continent. At this scale, you see smooth coastlines, mountain ranges represented by shaded bumps, broad rivers as thin blue lines. The rules at this scale are about topography, climate zones, and political borders. Now, take a magnifying glass and zoom in on a single kilometer of coastline. The smooth line becomes a jagged fractal of bays, inlets, and rocks. New rules become relevant: tidal patterns, erosion, the ecology of the intertidal zone. Zoom in further to a single grain of sand on that beach. Now you see crystals, microscopic shapes, the world of mineralogy and atomic bonds. The rules are now those of chemistry and solid-state physics. All three views are of the same reality. The continent is not less real than the grain of sand. It is a valid description at its own scale. Today, we learn how phi produces this multi-scale map of the world, with different effective productions at each level of magnification. Here is the organizing puzzle of this part. We have a single, fundamental description of reality in terms of the phi field and its exact dynamical grammar. Yet, we successfully describe and predict phenomena at the human scale: the flow of water, the strength of steel, the spread of sound, using completely different sets of equations that make no mention of phi's microscopic details. Are these effective laws just convenient lies? Or are they genuine, derivable aspects of the phi grammar that come into focus when we zoom out? How does the grammar itself change its appearance with scale? The answer is one of the most powerful ideas in modern theoretical physics: the emergence of effective theories through coarse-graining and renormalization. This is not adding new physics, it is changing our descriptive focus. Let's walk through the conceptual steps. First, consider a system described by phi at the most fundamental scale we have, perhaps the Planck scale or the scale of quantum fields. The rules here are the full, potentially complex, nonlinear phi equations. They govern incredibly fine-grained details, rapid oscillations, and quantum fluctuations. This is the close-up view, where every grain of sand is visible. Second, we decide we don't care about every microscopic detail. We want to describe the system at a larger scale, with a lower resolution. We do this by averaging or coarse-graining. We define a new, smoother field, which we can call phi bar. Phi bar is the average of the fundamental phi over a small region of space and time, like the average color of a pixel in a digital photo, which blends many individual grains of light. The rapid, fine-scale fluctuations of phi are averaged out into a smoother picture. Third, and this is the magic, we ask, what are the dynamical rules for this new coarse-grained field phi bar? They are not the same as the rules for phi. When you average a nonlinear equation, you don't just get the same equation for the average. New terms appear. Some microscopic details of phi get absorbed into defining effective parameters for the phi bar theory. For example, the myriad collisions of molecules, microscopic phi dynamics, get averaged into a single number, the viscosity of a fluid, a macroscopic parameter in the Navier-Stokes equations for phi bar. This process of deriving the effective, large-scale rules from the fine-scale rules is called renormalization. In our linguistic metaphor, it is grammar simplification. A long, convoluted sentence full of subclauses, the microscopic description, is paraphrased into a shorter, clearer sentence that captures the main point, the macroscopic law. So, we get a hierarchy of effective theories. At the smallest scales, the UV complete theory, UV for ultraviolet, meaning high energy, short wavelength. Rules are quantum, detailed, and fundamental. Phi is everything. At intermediate scales, effective field theories. Rules are classical or statistical. The field is a smoothed phi bar. Parameters like mass, charge, stiffness, and viscosity appear, encoding the averaged effect of microscopic physics. At the largest scales, highly coarse-grained theories like fluid dynamics, elasticity, general relativity as a theory of space-time geometry, and even ecology or economics. The field might be population density or price, which are incredibly distant but still logical descendants of patterns in the original phi. The crucial point: all these levels are speaking the same language. The macroscopic laws are not independent. They are forced upon us by the microscopic phi grammar when we ask the right large-scale questions. The smooth coastline is not an illusion. It is the real large-scale shape that emerges from the cumulative effect of countless grains and waves. Let's explore the triunity of this hierarchical production, the time echo of hierarchy, separated timescales. Different levels operate on different characteristic times. Electrons orbit an atom in femtoseconds. Molecules vibrate in picoseconds. A cell divides in hours. A forest grows over decades. The time echo is this separation of rhythms. The fast microscopic dynamics, Phi's rapid fluctuations, average out to provide a stable, slow background for the higher level dynamics, Phi bar's evolution. This allows for the persistence of higher level entities. A cell can exist for days, even though its atoms are in constant, frenetic motion. The space echo of hierarchy, nested structures. Space is organized into nested domains. Quarks are inside protons, inside atoms, inside molecules, inside organelles, inside cells, inside tissues, inside you. At each level, the relevant field describes the collective, averaged property of the constituents. The space echo is this Russian doll architecture. Each doll is a stable configuration of the dolls inside it, a persistent pattern in the phi field at that scale. The motion echo of hierarchy, emergent kinematics. The motion of entities at one level is governed by forces that are effective descriptions of the collective motion at the level below. The flow of a fluid, macroscopic, is the average drift of its molecules, microscopic. The force of friction, macroscopic, is the cumulative effect of electromagnetic interactions between surface atoms, microscopic. The motion echo is collective drift, the coherent movement of an ensemble that obeys simpler rules than the chaotic dance of its parts. Now, let's locate this organizing principle on the master tree. We are at the root of Book 9.6, Hierarchical Generation, a new trunk growing from the core of Episode 9. This node, scale-dependent productions, depends on the entire generative grammar. We need the fundamental rules to have something to coarse grain. It enables the rest of the book: the study of effective laws, renormalization as grammar simplification, and the reading of reality as hierarchical parse trees. It is the bridge from the fundamental, possibly unknowable, intricacies of phi to the structured, comprehensible world of human experience and science. To ground this abstract ladder of description, let's light lanterns from clear examples across science. A near lantern from material science: the elasticity of a rubber band. At the microscopic scale, the rubber is a tangled network of long polymer chains. The fundamental rules are quantum chemistry, the bonding and van der Waals forces between atoms. This is chaotic and complex. But when you stretch the rubber band, you don't think about atoms. You use Hooke's law. Force equals a constant, the spring constant K, times the extension. Where does this simple linear law come from? It emerges from the statistical mechanics of the polymer network. Stretching the band reduces the entropy of the tangled chains. They resist because they want to return to a more disordered, higher entropy state. The spring constant K is an effective parameter that summarizes the collective effect of billions of atomic interactions into a single number. The macroscopic law, Hooke's law, is a scale-dependent production of the microscopic phi grammar of chemistry. Middle lantern from thermodynamics: the ideal gas law. A container of gas contains n molecules, each bouncing around chaotically. The microscopic rules are Newton's laws, or quantum scattering for each molecule, an impossibly complex system to solve. But at the macroscopic scale, we have the simple equation: pressure P times volume V equals N times a constant Kb times temperature T. This law emerges from averaging the microscopic motion. Pressure is the average force per unit area from molecular impacts. Temperature is proportional to the average kinetic energy of the molecules. The perfect simplicity of PV equals NKBT is a stunning example of how messy microscopic details average out to a clean, universal macroscopic rule. A far lantern from particle physics: the Fermi theory of weak interactions. Before the electroweak theory and the discovery of the W and Z bosons, Enrico Fermi described certain radioactive decays, like beta decay, with a simple contact interaction. Four particles interacted at a single point with a strength measured by the Fermi constant, Gf. This was a brilliant effective theory. Later, the deeper theory, electroweak unification, revealed that this interaction was actually mediated by the massive W boson. The Fermi constant Gf was not fundamental. It was an effective parameter related to the more fundamental electroweak coupling constant and the W boson mass. Gf is proportional to that coupling squared divided by the W mass squared. At energies much lower than the W mass, the boson is too heavy to be produced, and its effect is to create the point-like interaction of Fermi's theory. The effective theory, Fermi's, is what you get when you zoom out to low energies from the more fundamental theory, electroweak. This is renormalization and effective field theory in action in the core of the Standard Model. From a rubber band stretch to the behavior of gases to the very laws of nuclear decay, a unifying principle shines. Microscopic complexity, when averaged over appropriate scales, crystallizes into macroscopic simplicity with new effective laws and parameters. The grammar simplifies as you zoom out. What then is the specific language role of scale-dependent productions? They are the grammatical rules of paraphrase and summarization. They are the set of operations, coarse-graining, averaging, renormalization, that allow us to translate a dense, detailed story written in the fundamental phi language into a shorter, more focused story that captures the narrative relevant to a particular scale of interest. It answers, how do we extract the forest from the trees, the coastline from the grains of sand, using only the rules of the original language? The core question this part asks about phi is, how do the dynamical equations for the phi field transform when we average over small-scale degrees of freedom, and what new effective equations and parameters govern the resulting coarse-grained field at larger scales? We are moving from the fundamental script to its many possible abridged editions. What do these hierarchical productions do for our understanding? They explain the success and autonomy of the special sciences, chemistry, biology, geology, etc., without needing to invoke new substances. They provide a rigorous method for deriving continuum laws, like fluid dynamics, from discrete or molecular foundations. They justify the use of different models for the same system at different scales: quantum versus classical, molecular versus continuum. They reveal which microscopic details are relevant for which macroscopic properties. Now, stability and breakdown. The framework of effective theories and renormalization is a cornerstone of modern physics. It is stable and predictive within its domain. It breaks down when we try to use an effective theory outside its scale of validity. For example, using fluid dynamics to describe a gas at very low density, where the mean free path is large, fails. You need the kinetic theory of gases. Using Newtonian gravity near a black hole fails. You need general relativity. The hierarchical picture tells us that each level has its domain of applicability, defined by the scale at which it was coarse-grained. Pushing beyond that domain requires zooming back in to a more fundamental description. This brings us to our empirical commitment: falsifiability. The claim that macroscopic laws are effective theories, derivable from a microscopic phi-based description, is a profound and testable hypothesis. The central claim: for any well-defined macroscopic physical law, for example, the Navier-Stokes equations for fluid flow, Fourier's law for heat conduction, Ohm's law for electrical conduction, there must exist a procedure starting from a plausible microscopic phi model that 1. Derives the correct form of the macroscopic equation. 2. Provides expressions for the macroscopic transport coefficients, like viscosity, thermal conductivity, electrical resistivity, in terms of microscopic phi parameters. These predicted coefficients must match, at least in functional form and scaling, the values measured in real materials. A concrete measurement scene: thermal conductivity of a crystalline solid. Consider a simple crystal, like solid argon. At the microscopic level, we model it as a lattice of atoms connected by springs, an approximation of the interatomic potential, a phi-based interaction. The atoms vibrate. Heat is the random vibrational energy. We want to derive the macroscopic law of heat conduction. Heat flux is proportional to the temperature gradient, Fourier's law. The constant of proportionality is the thermal conductivity, kappa. We perform two sets of measurements. First, we use neutron scattering to measure the microscopic properties: the atomic masses, the spring constants from phonon dispersion relations, and the scattering rates of these vibrational waves, phonons, by defects or other phonons. Second, we perform a macroscopic experiment. We create a temperature difference across a sample of solid argon and measure the heat flow to directly determine its thermal conductivity, kappa exp. The pass condition, validation. Using the microscopic parameters from neutron scattering, we employ kinetic theory or Green-Kubo methods, standard coarse-graining procedures, to calculate a theoretical thermal conductivity, kappa theory. This calculation involves averaging the chaotic microscopic phonon dynamics. The predicted kappa theory matches the experimentally measured kappa exp in both magnitude and its temperature dependence. For example, it might decrease at high temperatures due to increased phonon scattering. This demonstrates that the macroscopic law, Fourier's law with a specific kappa, is indeed an effective description emerging from the average microscopic phi dynamics. The fail condition, falsification. The calculated kappa theory, based on the best microscopic measurements, systematically disagrees with the macroscopic measurement by orders of magnitude, or predicts the wrong temperature dependence. Even worse, if we find that no reasonable microscopic model of the solid can produce a macroscopic equation that looks like Fourier's law, perhaps heat flows in a non-diffusive wave-like manner at all scales in this material, then the claim that Fourier's law is an effective theory for this system fails. It would mean the hierarchical bridge from microscopic phi to macroscopic heat flow is broken for that material, demanding a radical new understanding. This falsifiability ensures that the elegant idea of hierarchical generation is constantly tested against the hard numbers of material properties. Let's cultivate a practical recognition skill. You can train your mind to recognize hierarchical thinking in any situation where a system can be described by different, self-consistent sets of rules depending on the level of detail you care about, and where the higher-level rules are simpler but less detailed. Watch a traffic helicopter report. The reporter describes traffic as a slow-moving stream on the highway with a blockage at the 5th Street exit. This is a coarse-grained, fluid dynamical description. A driver on the ground experiences the microscopic reality: individual cars, lane changes, brake lights. Both descriptions are valid. The traffic flow is an effective field emerging from the interactions of many cars. Observe an ecosystem. An ecologist might model predator-prey populations with the Lotka-Volterra equations, using parameters like birth rates and interaction strengths. A biologist studies the behavior of individual animals. A chemist studies the metabolism inside their cells. Each level has its own effective laws, all ultimately arising from the physics of the constituent parts. Consider a corporation. The CEO sees balance sheets, market trends, and organizational charts, high-level effective descriptions. A manager sees team dynamics and projects. An employee sees their specific tasks and tools. The health of the company is a macroscopic variable that emerges from myriad microscopic interactions. Whenever you see a system that can be understood through different, nested layers of description, each with its own simplified rules, you are seeing hierarchical generation. You are seeing scale-dependent productions of a single, complex story. We must connect this foundational insight deeply to our Holophase journey. In the previous book, we saw the universe as a chaotic, novelty-generating computation. That left us with a problem. How do we find stability and order in that storm? Hierarchical generation is the answer. The chaos and novelty at the microscopic level, when averaged, produce stable, effective laws at macroscopic levels. The storm at the level of molecules creates the gentle, predictable pressure of the atmosphere. The generative grammar is not just creative, it is self-organizing into intelligible layers. If you want to see the full mathematical derivations and exact equations behind this idea, the techniques of coarse-graining, the renormalization group flow equations, the derivation of hydrodynamic equations from kinetic theory, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and appreciate the significance of entering Book 9.6. We are now learning how the universe's story organizes itself into chapters, sections, and paragraphs. We are moving from the syntax of individual sentences to the structure of the entire book. In the next part, we will deepen this exploration by looking at a specific and powerful example of hierarchical generation: effective laws and their domain. We will see how renormalization acts as a systematic grammar simplification procedure, flowing from detailed rules to simpler ones as we zoom out, and how this flow defines the boundaries where one effective theory must hand off to another. Before we end, the mandatory zoom out to hold our scope. Scale-dependent productions, effective laws, coarse-graining. These are all ways of talking about patterns in phi and their relationships across scales. We have added no new substances. We have simply learned to read the same text, the story of phi, with different lenses, focusing on the plot summary, the chapter outlines, or the individual words as needed. One field phi, plus its infinite tower of derivative questions, plus the principle of scale-dependent paraphrase. From this, the layered, comprehensible architecture of reality is built. As we conclude, hold the image of the geographical map. The continent, the coastline, the grain of sand. They are not three separate things. They are one thing, seen at three different magnifications. The holophase universe is this map. The fundamental phi field is the substrate, the paper and the finest possible ink. The quantum whispers are the molecular structure of the ink. The cosmic paragraphs are the shapes of the continents. And every scale in between, the chemistry of life, the flow of rivers, the orbits of planets, is a valid, effective description produced by the grammar when we choose the appropriate zoom level. We are learning to be master cartographers of this one infinite map. Salam, and peace be upon you.